So we're definitely now starting into the wavelet book. Our starting point, of course, is the idea of a filter, which is much, much older and more widely used and generally more fundamental than wavelets. But it leads us to wavelets this way. So we're going to, today this lecture focuses on individual filters. Then we'll see, well, those do wonderful things to a signal, but they're not so easily invertible. You lose information when you filter. And so if you want a transform that has an inverse, we'll see that to combine a couple of filters is one is a very neat way to do it. So this use of the word banks simply means that we have two or more filters acting together. So this is what's coming. So this is coming. This is coming. And this single filter is now. Okay. So filter banks coming actually probably in the very next lecture. So the syllabus as I had outlined it, I think I can say what I want to say about filters in this lecture and then move ahead to filter banks right away when we meet again. Okay, so a filter is a convolution. I guess I point out here that we're using the word filter in a different sense, I think, than Kalman filter, which was the subject of earlier lectures. Maybe there is somehow a common theme, but here I wanted to make that distinction, though. The filters I'm speaking about are pure convolutions. Here's the input signal. There's the input. There's the filter coefficients chosen. And that's where to choose. The input we can't choose. It's whatever comes to us. And, of course, this is the output. So I could, if I wanted to draw a filter, a block diagram, I would think there's the input, goes through some filter H, and the output is Y. Fine. Okay. And so what this filter does is a convolution. And I'm going to, you can see, well, I've used n for now. This is a different n from the previous lecture, I guess, because the signal is infinitely long. We're not in the finite, periodic, cyclic case now. We're in the whole line case, the whole discrete line case. So x, I have to express this as a matrix, of course. So here's the output, y of 0, y of 1, y of 2, and so forth, y of minus 1, and forever. So that's my first point, is that we're looking at vectors with no start and no finish. And we are multiplying by a tuplets matrix the vector x0. Okay, and you've seen this already in these lectures. And what's the matrix? The matrix, well, if I just look at y of 0, when n is 0, let's remember some words that we used before. This filter has finite length. There are only n plus 1 taps, n plus 1 coefficients. So this filter is an FIR filter, finite length. And also, it acts only on earlier signals, samples earlier or at the same time as the output. It's not a look-ahead filter. So it's FIR and causal. The cause X comes before the response Y. This is it. I'm in the time domain here. This is K is, I'm in a discrete time domain. Discrete time. From you know, all -2, -1, all integer. I'm taking the sampling period to be 1 for simplicity. So I have samples at all integer times. And I act on those with this filter H, which multiplies x of 0 by h of 0. Right? These, of course, everybody says. I mean, I even highlighted with yellow this fact that we've got K, the two indices add to this one. It's a convolution. It's a linear time invariant. I should put all this down. It's FIR, it's causal, and it's linear time invariant. Well, I'm squeezing key facts, but they're all evident here. Okay, I just want to complete this matrix. So y of 0 is h of 0, x of 0, then h of 1. Notice it's going to be lower triangular and tuplets. Might as well anticipate what's coming. That h of 0 multiplies x of n. When k is 0, h of 0 multiplies x of n. H of 1 multiplies x of n minus 1. So h of 0 will sit on the main diagonal multiplying x of 2 to give the to contribute to y of 2. But then there'll be an h of 1 on this diagonal. You see that? H of 1 multiplying x of minus 1 into y of 0. H of 1 multiplying x of 0 contributes to y of 1. H of 1, x of 1 contributes to y of 2. So the matrix is tuplets. And we can understand that, and the matrix is completely, let's quit it let's quit while we're ahead at 2. Suppose I just have 2 taps, h of 0, h of 1. Let's take short filters, crude filters. What could we achieve with a 2-tap filter? Okay. So written out in full, y of n is h of 0, x of n plus h of 1, x at n minus 1, and that's all we're doing. So there's a 2-tap filter, and therefore just 2 diagonals in the matrix. How should we understand the action of such a convolution? So that is a convolution. That's a convolution of something that only has 2 components, h, with something that has doubly infinite components. But what does it do? What does it do, for example? Let's just take examples. Suppose they both equal a half. H equal the 2 components are both a half. So y of n is 1/2 x of n and 1/2 of x of n minus 1, the previous sample. So it's a running average. can we just consider that example? Because it's a very useful one to consider. How should we look at that? Well, it's natural to ask, I can hardly avoid now going into the Fourier domain, looking to see, because it's constant coefficients, looking to see what it does to exponentials. Can I do that? Well, first of all, what does it do to zero frequency, to the DC term? Suppose the input is x all ones, constant DC input. What's the output? Same thing. So I'm seeing this as a low-pass filter, because this is omega equals 0, passes through the filter with no corruption. Omega equals 0. I'll introduce omega properly, but 0 frequency certainly corresponds to that input. Okay, tell me the other extreme. What input would be wiped out by this filter? Alternating one. Input. So a second input of special interest is that alternating one. 1 minus 1, 1 minus 1. And that leads to y equals, what's the output for that? Of course, that continues forever, so it doesn't spoil our beauty here. Y comes out as 0. Okay. Okay. And what frequency, now let's allow that word frequency to begin to sneak in even more. This, to me, is the frequency omega equal pi. And that's the fastest oscillation, the highest frequency I can have. My Fourier transform is, it's also omega equal minus pi. Those two are identical. In other words, I'm using that discrete time Fourier transform that takes, well, so it's a discrete time. So in the frequency domain, I'll use capital X for the transform of the input little x. So what is that transform? Capital X depends on frequency. Little x depends on time. And the transform is, these are the coefficients of a 2 pi periodic series e to the minus I, or j, omega n. And I add. And all n's now are, my signals are infinite. That is the discrete time Fourier transform. I start with discrete time signal, and what kind of a result have I got here? What kind of an object is this Fourier transform? It's a function. So a function of frequency. And what's the range of frequencies? Well, this thing is 2 pi. It has period 2 pi. So it's normal to take the range of frequencies to be minus pi to pi. So let me do that. Let me do that. So it makes the figures nicer if I go from this is frequency here, from minus pi to pi. And somehow what I want to plot is, for this example, is at omega equals 0, somehow the multiplier, the gain, the frequency response function was just 1 at omega equals 0. This is omega, a frequency, but it's going to be periodic. So this is the highest frequency, and everything happens on this level of length 2 pi. Now, this is telling me that the frequency, that the response at this frequency is 0. So maybe I use yellow to plot those key points. I'm talking here about a low pass. This is going to be a low pass filter. This averaging, this running average. Running average. Okay. What's up at the other frequencies? What's the input and what's the output at other frequencies? Okay. I'm looking for, I guess I'm looking for an eigenvector. This was an eigenvector with eigenvalue 1, just came right out. This was an eigenvector with eigenvalue 0, right? It was actually a null vector. And notice, this is telling us then that we cannot invert this filter. This matrix now, which is 1/2, let me put those 1/2 in there, is a very simple matrix, but it's not invertible. So 1/2 is sitting on the diagonal all the way, and 1/2 is sitting below the diagonal all the way, and otherwise zeros. And that's the main diagonal there. And that matrix doesn't have a bounded inverse because we found a vector that it kills. Okay. Now, what are the eigenvectors? Maybe, I mean, it's sort of weird to be asking about eigenvectors here, but maybe the main point is that when we have a constant coefficient linear operation, the eigenvectors are always the same guys. That's somehow, and therefore that's the way to study every constant coefficient linear operation. You have to study it because by those eigenvectors, which are always these pure frequencies, these pure harmonics. So let x omega of n is this pure frequency e to the I omega n. So this is there's a pure, so these are the components of the vector. It's a harmonic, discrete harmonic, because it's these n, the n is discrete time. But this was omega equals 0, then all the components were 1. This was omega equal pi. What are all the components of this thing when omega is pi? Do you see that this is the right thing? If omega is pi, what have I got there? Omega is pi, then e to the I omega n is what? Yeah, if omega is pi, then I have e to the I pi, which is minus 1 to the nth, which is exactly our alternating guy. And in between, for these other omegas, in between omegas, we've got, well, but little problem here. What's my little problem on the graph? I've got complex numbers. Only for these two cases, all ones and pure alternating, then I got real numbers, so I started off with this graph so happily. But, yes?
I'm confused about this.
Sure.
Say, once again, what is that a graph of?
Yeah, well, that's what I have to. That's what I have to tell you now, because I have to. No, that's fine. That's exactly. What shall I graph? And I've got a little problem because I only graph something real. So let me think a little bit more about these to see what it ought to graph. Yeah. Okay. What am I graphing? What is the? If this is the input, what's the output? That's my question. That's really my question. If my input is a vector of is this pure frequency, omega, what's the output? Oh, well, I'll just plug it into the formula and figure out the output. Here you go. This one is easy, right? Okay, x of n is e to the I omega n. I'm taking a pure frequency. And what's x of n minus 1? E to the I omega n minus 1. So that's what the filter is doing to this pure frequency. And now, how do I want to write that? How do I want to understand that? I could, yes. Let me just get an e to the I omega n out of it first. So what do I get times an e to the I omega n? Well, 1/2. And what's the other one? 1/2 of what's e to the minus I omega. Well, there's the most important function. That function's got it. It's got the total information about the filter. It's got, because it shows us the 1/2 and the 1/2. And this is the frequency response function. And I'll call it h, using the same letter h, of omega. Well, actually, I used capital X of omega for the transform of the discrete x's. Is my notation consistent? I believe it actually is. This h of omega is nothing but h of omega is nothing but the sum of the h of k's e to the minus I k omega. Yeah, I'm jumping from the example where it's 1/2 and 1/2, and we did everything really clearly, to what it would be for for any set of numbers. Can I say what I'm trying to say in one sentence? What's up? What's up is this formula. That this convolution in time domain goes into a multiplication in the frequency domain. There's the big deal. That's the most important formula in this subject. So in the time domain, we have little x's, we have little h's, and out come little y's by convolution. In the frequency domain, we have big x's, big h's. We multiply ordinary multiplication, because in the transform domain, and out comes big Y. And of course, this is the way to understand the filter. And Oppenheim's book would never have written that matrix at all. Is that, like, sensible? What is this? I mean, the first page of, or the first 2 or 3 pages of the wavelet book check this, that just check that if we start in the time domain and we define the frequency that transforms the capital X, capital H, capital Y, that the convolution in the time domain gives us a multiplication in the frequency domain. Right. Most important formula, surely. Surely. And that's, so this is what we ought to graph. This is what we ought to graph, but it's complex. Here it was. It's complex numbers. So what's the best to do? Graph its magnitude. So that now we finally say, what are we graphing? I'm going to graph the magnitude of h of omega. I'm losing the phase in this graph. I would have to do a separate graph of the phase. So if I really want h of omega, I have a graph of magnitude and a graph of phase. I'm just, you know, I'm breaking h of omega into its magnitude times its phase, e to the I phase of omega. And I don't, magnitude is good enough for now. What would the magnitude be in this example? What's the magnitude of that? So you said it as soon as I wrote that up there. What's the magnitude of that? Is it the cosine of something? How do I see that that's the cosine of omega? Is that really the cosine of omega over 2? Oh yeah, I multiply it by what? Right, I multiply it by e to the I omega over 2, and that doesn't change the magnitude. That changed the phase. That added omega over 2 to the phase. But if I multiply it by e to the I omega over 2, the magnitude doesn't change, and then what do I have? So the magnitude won't change if I do that. A half of e to the I omega over 2, and then when I multiply this one, that leaves an e to the minus I omega over 2, and then that's the cosine of omega. Yes, thanks. So that's exactly right. Magnitude of h of omega in this example is, well, can I graph the cosine? What does it look like? It's one loop of the cosine, right? It's sort of like parabola, is it? But it's not a true parabola, right? Yeah. Okay. So I'm graphing the cosine of omega over 2. And what kind of a filter is that? If I look at that filter, it's low pass. It's a low pass filter because low frequencies go through more or less. High frequencies get killed more or less. It's a very crude low pass filter because there's a big region which is fuzzy. So if I really wanted, which I very often do in applications, given the signal, I want to find the part of it that has a certain range of frequencies. Say a low pass filter, but a heck of a lot better than this one. What would be a, let's draw a better low pass filter. But I'll keep it low pass for the moment. Okay? So what would a better low pass filter do? It'd be from minus pi, 0, and pi. So I'm going to graph h of omega, and what would a really good low pass filter do? Suppose I wanted to keep all the frequencies between there and there. So some omega pass, omega p, and minus omega p. And suppose I want to kill all the frequencies. I can't kill, ideal low pass filter. Ideal low pass filter would be like this. Look. That's ideal. Perfectly keeps all these frequencies, perfectly kills all those. That's an ideal filter, and that's a graph of h of omega again, which is the sum of h of k e to the minus ik omega. Okay. Well, certainly we would be very, very happy to construct such filters, because that means that we can take any you give me an input, and I take out all the high frequencies and keep the good ones, keep the good stuff. But what's the trouble with that filter? That I can't. It takes a long time because, right, because there's no finite. I mean, if that's a graph of this, I need k all the way from minus infinity to infinity. I didn't want to do that. For an ideal filter, it would be IIR, infinite impulse response. So that I could stand for infinite and also for ideal. Yeah?
On your other low-pass filter, I sort of doubled my frequency so that it all being like constant numbers. Am I saying, was that not happening?
Is there...
When you're just adding the numbers, subtracting the numbers, just adding them together?
Let's see. When I'm... If I'm adding... I'm not sure what you're adding. So this is what my... What this... Were you asking about this filter? Okay. So it computes the average. Now in the frequency domain, it wipes out omega equal pi, because that's the alternating guy. If my input was a sum of... Yeah, that's a good question. If my input was a sum of a DC term and a pure alternation. Yeah, but it's a good. What would be the input? So what input would I be talking about then? Suppose I add the inputs for omega equals 0 and omega equals pi. So there's another good example. So what input would that give me? 1, 2, 1, 2, or 0, 2. 0, 2. Yeah. Right. If I literally added them, it'd be 0, 2, 0, 2, 0, 2. And what would the output be? All ones. It's beautiful, isn't it? Keeps averaging those zeros and twos, and the average would, and the output would be all ones. Right. Right. That's right. Yeah. Now that's a good example. Yeah. So this is not a pure frequency. It's a sum of two frequencies, right? Yes, right, right. Yeah, that's right, right. Okay. So where did we get to? We got to this ideal filter, but we couldn't implement it. Now, what to do? This is certainly the problem that everybody faced as they started creating filters. We want this, but it's asking too much. So what shall we do? Well, the natural idea is take these. We could figure out these numbers, right? Because this is the Fourier series of that function. Oh boy, I better say that again because I just thought of it. There's our function, and here's its Fourier series. And we know the Fourier coefficients of a square wave. They die off at what rate? Just linearly, just 1 over k. It's bad news. So if we truncate this at 1,000, we're still throwing away pretty big stuff. And we would have a tremendously long filter. And what would it, suppose I go from minus 1,000 to 1,000, and I use these same numbers. Well, even, let me do 100. I'm going to have trouble enough with that. Suppose I just truncate. Is that a good idea or not? In order to, it should be somewhat ideal, right? In a way, it's the optimal. It's the idealist filter we could create in some sense. And what would the picture look like? Yeah. What's the So now I have another function chopped at 100. And what's the graph of the function look like? It has the Gibbs phenomenon. This is exactly what the Gibbs phenomenon is. Take the Fourier series for a true step and chop it. So if I graphed this, it would be really accurate here, but it would get worse and worse. Worst, of course, right there. Then it would do a pretty good job, drop down, and then it would. There'd be a little envelope of ripples there that would be unpleasantly large right at that frequency. All right, so filter designers, this is actually the closest function, this Ripley guy, this polynomial. So that's a polynomial of some degree 200 or so. And of course it goes the other way too. Same, it's going to be symmetric. Now, in what sense is that Ripley Gibbs unpleasant looking, or a little sort of, worrying, because this height is a fixed number here. In what sense? I said it was really the best possible in a certain sense. And what is the sense in which that's the closest function to the ideal? In L2, right. If I measure the error, the difference between those two functions, and integrate the square, I've got it as small as I can get it. Because that's Fourier, because this is an orthonormal basis. And if I take an orthonormal basis, in the L2 norm, everything, it's a pure projection, use the same numbers and just set the other numbers to 0. That's L2. So there you're seeing an advantage of L2 that it's so nice to compute with. We didn't have to, all we just did was truncate. But the drawback is, point-wise, it's not perfect. Okay, suppose I wanted, so now tell me what a different filter designer might come along and say, well, the filter you want is what? What would is not going to be optimal in L2? What measure would be another possible measure to use? So how could I measure this error? One way is to measure its energy, the L2. But another measure of the error is the max difference. Right. So the biggest ripple there is killing us in the max norm. So in the maximum norm, this would be this would have a much higher error, namely this Gibbs number, which is known to. Actually, it's interesting. Gibbs's first paper, his papers on his own phenomenon are like, the first paper is about 1.5 pages, and he gets it wrong. He missed it. And then 6 months or so later, well, of course, a correction was published that it has only about 10 lines, where he says, I just missed it there. And then he tells us that it goes up here, and he tells us what that number is. It's some integral of something, and we can find it to any number of places. And so it's sort of, it's the most famous phenomenon in signal processing in a tiny, tiny paper that was a correction to a quite short paper. Anyway, if we're looking at the max error, we want to reduce it there at the cost of raising it there. So we could reduce it there, but then the ripples wouldn't die off as fast. And what's the optimum if we're looking at the max error? Equi-ripple. So the optimum error in the max norm, meaning the worst frequency, is equiripple. What does equiripple mean? It means that I'm graphing a polynomial of degree 200. It's got 200 ripples, and they all have the same height. I guess in magnitude, I can't let them go below 0 here. They do, yeah. So that's the equiripple filter, and that. Now, how would you find the coefficients for that one? So now this is H100 equiripple. That's not so easy. You're looking for the polynomial that, and it's not even automatically clear that there is one that has equal height ripple all along there. Of course, there's got to be an error here. Actually, to get anywhere, we really have to allow ourselves a little space between the end of the pass band and the start of the stop band. So if I give these numbers to MATLAB, MATLAB would want two numbers. The MATLAB, so what's the MATLAB command? Remez, I think, because it's this guy's algorithm. So remez.m would be the MATLAB command, which would, so what would it do? You would tell it omega p and omega s. So the inputs would be omega p and omega s, and you could input the degree, 100. And stop, S for stop. At your choice. It's some distance here, and the more distance you give it, the easier the design problem. The lower the ripples, the closer you can come to ideal. If we fix the degree, then if you're asking this polynomial to ripple and then get down like mad and ripple again, if you tighten that will sort of, there's a relation between the 100 and the ripple height delta. Yeah, I mean, you can't get them. No, you can't get them both. So somehow there's a relation between. Shall I call this degree n? So there's a relation between n, the number of coefficients I'm allowing, the omega s minus omega p, the width I'm trying to do this in, and the delta, the error. And a student of mine pinned that down, I think, more closely. It was known, people did MATLAB experiments to get a graph of this relationship, but the theory is possible here. I'll just mention that if Oppenheim was sitting here, he would say, he would wait. He would allow. Let's see. He would want a smaller ripples in the stop band than in the pass band. So he would introduce a weight. So we'll allow W Oppenheim for a weight that allows you to unequally have unequal height ripples in the pass and the stop bands. But let's take omega. Let's set Oppenheim equal to 1 here. Okay. So what was my point? That these equiripple filters are the best optimal error in the max sense, and also that we have to go to MATLAB to so what will MATLAB output if we give MATLAB what we want? The coefficients, exactly. MATLAB will output the coefficients, and it'll plot the graph. And of course, it won't look like that. It'll look like this. Yeah. And and we know a relation between these, so that if we know what pass, stop, and passband we want, we know what degree we have to take to get a certain error reduction. Yeah. Okay, that's a discussion of filter design of, now, it's not a final discussion of filter design. I mean, this Oppenheim's course could ask other things. You might like combine so we've got two choices here: L2 least squares and max. But that's not the only two choices. We could average between those. We could introduce other error measures. All sorts of possibilities. But maybe that's a point to go to high pass. Let's look at the other extreme. What would be a high pass filter? What would its graph look like? And give me an example of a high pass filter. Give me an example of a high pass filter that kills zero frequency. So let's do a high pass filter in dotted lines. I guess I'm going to look for a filter that has h of omega is probably a sine of omega over 2. What would be a natural? How could I fix this filter? Change one of the signs, right? So I can easily change high pass to low pass, or vice versa, by alternating the signs. That's a point we'll see in filter banks that are coming. We'll have to get quite adept at playing with properties of filters. But so this is like that. I'll write that point down. From low pass to high, between low pass and high pass. One way, if I have one of them, alternate, well, reverse every other sign. I'll say it out in full here. Reverse every other sign in the sequence of H's. Yeah. You ought to think, why does that work? Think of what that means for capital H, because you really have to train yourself to think in terms of capital H, this function. Okay. Sorry? No. Let's see. What will it do? Yeah, what will it do? Maybe since we're doing that and I'm saying we should pay attention to it, what would happen there? And what do we want to do? Yeah. So I'm going to stay with that idea because it is important. So let's say our low pass guy is h of omega, which is by our rule is this one. Now, first, let me ask, what do I want to do to make that into a high pass filter? If I have this kind of a picture, and I don't know if my sign picture was correct at all. I want, yeah. So two ways to look at it. Either I said here, so now high pass will be, I claim that if I do a -1 to the k, h of k, e to the minus I k omega, that I've got a high pass now. But I don't see why from that. Do you? What have I done when I did this crazy -1 to the k? What have I done in the frequency domain? So I want to re-identify this as, what did I do to this thing? In the time domain, I did a -1 to the, yeah, here we go. Question finally focused. In the time domain, I did a minus 1 to the k. That's what I'll later call, for, in short, alternating the signs. What have I done in the frequency domain? Keeping the same k, but changing the frequency. It's the same h of k's. Now, it's a phase shift. By what? One or the other, because it's the only... Well, we could... Okay, well, let's see. What do we want to do? We want to move omega equals 0 out to pi. Don't we want to shift by pi? What was 0, we want to be pi. What was pi, we want to be 0 or 2 pi. Yeah, so it's this, and of course, minus 1 to the k is what? Is e to the I, or minus plus or minus I pi k. So we just, it's just omega plus pi or omega minus pi. E to the I k. You see, we've got, well, maybe minus e to the I. I'm kind of getting myself tangled with minus signs here, but the whole point was, this is, what's the word for that when you shift the frequency? That's a modulation. We've modulated in frequency domain, and we've multiplied by e to the I pi something, e to the I k something in the time domain. Yeah. So this is what happened in the time domain. That's what happened. That's the modulation in the frequency domain, and that's why this rule of alternating signs. Yeah. Yes. Okay. I think we should call both modulation. Yeah. I mean, because it's the same. I mean, it's the same operation seen in two domains. So let's call it modulation, right? Modulation. Phase shift. What I mean, modulation, phase shift, all those words. I don't know how you feel about these things. It's like, on the one hand, it's elementary what we're doing here, but on the other hand, you have to think it through, and it's so important. You know, and it just uses again the fundamental facts of the whole of the Fourier thing, but it's so important. Okay, so this is, now we know how to get from low pass to high pass. I guess in the lecture outline I used the word band pass. So let's just know what that word means. What would be an ideal band pass filter? Well, in the frequency domain, of course. I can't ask you such questions in the time domain. I wouldn't have the slightest idea. What would be a typical band pass filter? Okay, what are we trying to do? We're trying to create a filter that selects a range of frequencies. Like, suppose we know we're looking at heartbeats, and we want to pick out, you know, a range of frequencies there, or we're looking at electrocardiogram. I mean, or an electroencephalogram for epilepsy. We want to pick out a range of frequencies that's physically significant. Say this range. Okay, then what's the ideal bandpass filter? Well, you know it before I draw it. 0. Okay, there maybe in many cases it would very often happen that we would be looking at real coefficients, and it would be it would be very common that we would have a symmetric thing around 0. So there would be a bandpass filter, or just one of them. I'm not a good enough engineer to know which one to design. MATLAB, I guess, would design that for us again. well, it's not going to design the infinite one. We could find the coefficients for it. We could truncate it. It would have a Gibbs phenomenon again, so it wouldn't be that great probably. And but MATLAB, with a different algorithm, could find an equiripple bandpass filter. The error would ripple. We'd have to accept an error delta. That would depend on n. Right. Okay. Well, that's a lot of discussion of filters, and there's more to say. Of course, there are people's names are associated with filters, or something called Butterworth filters. Those are IIR filters. How could we get an IIR filter? A typical IIR filter would be when h of omega is a ratio of p of omega over a q of omega, of a polynomial over a polynomial. So this is a rational. We use the word rational to mean ratio of polynomials. That would be, you see that would be IIR, right? Because it's not a polynomial. FIR is polynomials. So FIR filter is a true polynomial. This one is Q inverse P. This is an FIR inverse times an FIR. And those are quite valuable. Those are used a lot in statistics. In what's that called? Regression. Yeah, ARMA. What is that? Auto regression. Right. All that world. So there's interesting design questions for rational functions. Well, this is a major world. But my point at the beginning of the next lecture, so wavelets and filter banks really start 2 weeks from today. My point will be that we need more than one filter, because if we have a low-pass filter, it kills the high frequency. We can't invert that. We want with two filters. Yeah, here's the ideal filter bank, and then I'll stop. The ideal filter bank would be, I'll draw this graph again because it's always there. Okay, the ideal filter bank would be an ideal low-pass filter and an ideal high-pass filter. That would be beautiful, wouldn't it? What would be the properties of those two filters if we do have them, only they're IIR. So in goes the signal X. It goes through the low pass. So it comes out, we find its low frequencies, we find its high frequencies are totally separated. I mean, that's the ideal of every filter designer, to be able to do this in a nice way. And I guess those two vectors would probably be perpendicular to each other, because this involves only they don't share any frequencies. And pure frequencies are perpendicular, so I mean, that would be wonderful. But we can't do it. So we're going to have to settle for filters that are the low-pass filter. We'll have to, let me draw that in yellow. We'll have to, in some way, we'll have to deal with, we'll have to compromise. And the high-pass filter, if we choose it brilliantly, will compromise the other way. And the two pieces, the two outputs are no longer orthogonal because we've got overlap here. But still, we've got something valuable. We've got a pretty good separation of the input into low and high. Okay, so it's a lot of fun now coming up, the designing of filter banks. And if you have a chance then if you have a copy of the wavelet book, this would maybe be the right time to get it out and look at chapter 1. Okay, see you in 2 weeks then. Yes.